Hello and welcome back. This episode, we're going to cover 5 examples of derivatives, and we're just going to be covering polynomials, and we'll do a trigonometric examples, and then an exponential example, which will be a very special video in terms of example type videos. So let's go ahead and get into this. Anyways, first one that we're going to start off with is the derivative where f of x equals x cubed. So let's go ahead and start off by saying that f prime of x, so the derivative of this, is going to equal the limit h approaches 0, same format as every time. So the function of x plus h minus the function of x divided by h. This will give us our instantaneous rate of change. So let's go ahead and actually plug in f of x being x cubed. So, do all the busy work. X plus h cubed minus x cubed all divided by h. Naturally, first thing you always want to do, you always just want to expand the top term right there. So, I'm just going to do a quick expansion, x cubed plus 3 hx squared plus 3h squared x. I might do a video on quick expansions for polynomials like this, but for now, you can take my word on it, or you pause the video and figure it out for yourself by doing the actual multiplication. But anyway, I'll leave it like this. So now we have this whole expanded term right here, and what you notice is that the leading x cubed and the subtracted x cubed can cancel out. Every term right here has an h in it at least once. So that means we can cancel out everything at least one time when the h is long. So the h to the 1 goes to h to 0, which is 1. H squared turns to h to the 1. H cubed turns to h squared. So now when we write our limit, we're almost done. H approaches 0, we're going to have 3x squared plus 3hx plus h squared. And now, because the limit goes to 0, this term goes to 0 when we sub in h, and so does this term when we sub in h. Now, curiously, our limit equals 3x squared. Okay, that's alright. Let's just keep in mind that the 3 that was once up top came out front. Let's take a look at another example. We're going to look at the square root of x now. So f of x equals the square root of x. And I'm going to use now Leibniz notation. What is df of x by dx? That's how we'd say this out loud. df by dx. Well, same approach we do every time. Limit as h approaches 0. Let's just plug it in right away this time. No need to stall around like that. Minus the square root of x, all divided by h. Okay, so now we have this limit as h approaches 0. What we want to do is we want to rationalize the numerator. So let's go ahead and rationalize the numerator. If you remember from last time we did it, all we're going to do is just multiply by the conjugate of it. So now it's going to be plus root x at the end, and what that accomplishes is that will actually square each term individually. Alright, so let's go ahead and do that. So it squares each term individually up top. So that's going to be x plus h squared. So that's going to bring us to x plus h. And then it's going to do this term squared, which is going to be x. Nice. This cancels out with that. And then on the bottom, we're going to have h times that root x plus h plus root x. Now, what you notice is that there's only an h left up top because the x is canceled out. So we could just simply cancel out the h up top with the h on the bottom. For our final line, we have limit as h approaches 0. 1 over root x plus h plus root x. And when h turns into 0 here, it's going to be root x plus root x. So we have 2 square root x's. So it's going to equal df by dx. It's going to equal 1 over 2 root x. Now, another way to write the square root of something, square root of x, is to write it as x to the power of 1/2. Curious that we have a 1/2 term here for our polynomial. Interesting. Let's go ahead and do another example. It goes along these lines. Let's handle when we take the derivative. So now f of x is going to equal 1 over x. Now what we're going to do is we're going to do the exact same thing, f prime of x. Let's actually try evaluating what's the derivative at 3. That's what we're going to evaluate after this. We're going to figure out what the slope is of 1 over x at 3. You remember 1 over x kind of looks like this, so it's not going to be too big of a number. So f prime of x is going to equal 1 over x plus h. Almost forgot my limit expression right here. H approaches 0 minus 1 over x. I'm going through these 3 examples so that way you could see what it's like to handle a radical, what it's like to handle a reciprocal, and what it's like to handle just a normal sort of polynomial expression like the x cubed. So let's continue on with this reciprocal example. So what we want to do is up top, we see 2 fractions. Anytime you see 2 fractions being added together, always, always, always like denominators. This one is missing right here. This one is missing 1 over the x term over here. So what we're going to do is we're going to multiply this term by x over x. And this term is missing x plus h. So we're going to multiply this term over here by the x plus h up top and on the bottom. So when we accomplish that, write it out, lim h approaches 0 of 1 times x is just x up top there. Now they're going to have a like denominator, which is x times x plus h. And then the 1 times x plus h is just x plus h. All right. And this is, of course, all divided by h. So let's just simplify things out a bit. We'll distribute the minus term into here, and then we'll send this entire term right here. We'll send it all down to the bottom where it belongs. All right. So let's just go ahead and do that simplification. X minus h divided by h, x plus h. All right, looking good. See that these x's right here are going to cancel out. X minus x is 0. And now, like we had before, we have an h up top and an h on the bottom. Easy cancel out. But this is going to turn into a minus 1 because we still have that minus term right there to deal with. Now, we're going to have this expression after all that. Minus 1 over x times x plus h. Now we're free to plug in h equals 0, and it won't cancel things out. So now we'll have x times x. Well, that's going to equal minus 1 over x squared. And just to hammer the point home, one more time, 1 over x, which was our function, can be written as x to the minus 1. And look, the minus 1 term pops out right there. And in fact, right here, I'm going to write this down for a rule. F of x equals x to the nth power. What's going to happen is its derivative, f prime of x, is going to equal n x to the n minus 1. So let's look at how this worked out. So x to the minus 1 turns into minus 1 up front, and then x to the minus 1, which equals minus 1 times x to the minus 2. Hey, x to the minus 2, that equals minus 1 over x squared. Hey, that worked! Miraculously, of course the rule works. So this will be a lifesaver when it comes to polynomials. Now, let's take a look at what happens when we make things a little bit bigger. But first, let's just quickly go over an example of this rule in practice. Oh, I almost forgot that we're going to evaluate this limit at 3. So when we take f prime of 3 in this case, f prime of 3, the derivative at 3, it's going to equal minus 1 over 3 squared equals minus 1 over 9. Almost forgot to evaluate the slope, like I said we were going to do right here. Alright. So one more example, just so you get a feel for that polynomial rule. F of x equals 1 over square root of x. Okay, so this is going to equal, we know it's a reciprocal, so we could say it's to the power of minus 1. And then the square root, that's x to the 1/2. Minus 1 times 1/2, this equals x to the minus 1/2. So now, to find our derivative, f prime of x, it's going to equal minus 1/2, bring it out front, x to the minus 1/2 minus 1. Okay, so minus 1/2 minus 1 is minus 1/2 minus 2/2. So 1 minus 1 minus 2 is minus 3. So this is going to equal minus 1/2 to the x minus 3/2. Okay. Now, when we just apply this reciprocal right here, minus 1 over, let's center that 1. 1 over 2 x to the 3/2, and then the half is going to come out as a square root. We'll have this as our derivative. So the derivative of 1 over square root of x equals minus 1 over 2 square root of x cubed. So this could have been a long and tenuous process using other method with the limit, but now we have this simple process. And this isn't the proof channel, but I'm going to invite you to prove this for yourself. It's not too hard, and when we get to exponents, it'll be very easy. I'm not going to touch derivatives with exponents right now. All right. One more rule to make derivatives easier. Let's look at what happens when we find the derivative, this long polynomial. F of x equals 5x squared plus 2x plus 1. Wow, that's big right there. But it's actually not going to be too bad. Notice what happens when I go to use the derivative formula. Limit h approaches 0. So we're going to have this term for all of our x plus h's squared plus 2x plus h plus 1 all divvied out. And then we're going to subtract off of that 5x squared plus 2x plus 1, all divided through by h. What you're actually going to notice is that when the minus sign distributes in, you can rewrite this by pairing up. You could pair together this term with this term. You could pair up this term and this term, and you could pair up this term and this term. So really, instead of taking the derivative of this whole thing altogether, what I'm saying is that the derivative is really just the sum of each of these terms. Okay. So now we just have to figure out what is the derivative of 5 times x squared. Now here's another thing that happens. If we're looking at just the limit, the derivative I mean, of 5x squared, we have 5x x plus h squared minus 5x squared over h. This 5 is attached to both of them. What you could do is you could factor it out, leaving you with the limit as h approaches 0 of just x plus h squared minus x squared over h. So essentially, what's happening here is that when you have the derivative of something, so f of x can equal some number a times g of x, some number b times h of x, the derivative f prime of x is going to equal a times the derivative of g of x, g prime of x, plus b times the derivative of h prime of x. Okay, so we don't even have to worry about these coefficients out front. We just have to take the derivative of the x squared, the derivative of the x, and the derivative of the 1, and then we'll just add together those three derivatives. So I'm going to rewrite it in orange. What we're taking the derivative of, f of x, 5x squared plus 2x plus 1. So now, when we take the derivative of this, f prime of x, it's going to equal 5. Now, taking our derivative rule, 2 times x, 2 minus 1 is 1. So I'm just going to leave that as 2x plus 2. Bring the 1 out front, and then x to the 1 minus 1, x to the 0, which is 1. So it's just the derivative of 2x is just 2, which makes sense. If that was a slope equation, the slope is just the number being multiplied by the x. Makes sense. And then 1, the constant term, well, constants don't change. Their rate of change is always 0. So now we just quickly found the derivative of that term to be 10x plus 2. Now that is smart differentiation. I'm going to leave it at this one. Next time, we're going to be covering trigonometric derivations. Till next time, keep on learning.